Hello Pantheri and welcome to our new video. Today it's about derivation of a torque on a spinning sphere. The torque is here. The torque or a momentum is equal to minus 8.3 and times pi a cubed, eta and omega. Eta is dynamic viscosity, omega is the angular velocity of a spinning sphere, and a is its radius. So, shall we begin? Yes, actually, what do we need to derive this equation? Well, we have to solve Stokes flow equations, which are these. Stokes flow equations. Let we assume we know from the symmetry of the problem the fluid is moving around the sphere is rotating, so velocity should be proportional to phi unit vector. Next, also velocity should be a function, this magnitude should be a function only of rho and r. We can choose two of coordinates from a cross section with phi is equal to constant plane. So let's see r rho right here. The boundary conditions are very simple. At r is equal to infinity, velocity should vanish, far field is stationary, and at r is equal to a, the velocity is going to be the polar radii times omega. That's simple kinematic equation. Next, we will substitute in this form of solution into this, because this equation holds automatically, because if you take the divergence, you will get v with respect to rho dot phi, which is 0, v respect to r, which gives r hat, it's also 0 because they are perpendicular to each other, and there is also divergence of phi, which is 0, so that's automatically 0. So the first equation is solved immediately. Next, we have to compute this Laplacian. We will use a trick. Again, Laplacian of v can be written as minus curl over curl of v, because there is a rule which tells us that curl over curl is gradient of divergence minus Laplacian, so this has to be 0 because divergence of v is 0, so that's only minus double curl. Yes, so let us substitute in, it's minus curl of v. We will compute very easily because it's nabla acting on this and nabla acting on this Leibniz rule. So it's v with respect to r times r hat across phi, which is going to be r and phi. That's minus direction, so it's theta minus theta. V with respect to r minus theta and plus the second term will be v with respect to rho, which is equal to it's with respect to rho times rho hat cross phi hat. Rho hat cross phi hat is z hat because of this positive direction. It's z hat plus 1 over rho, because the cross curl of phi is 1 over rho times z hat, so that's plus 1 over rho v z hat. Yes. And first, let us notice that v is a function of two variables. We can simplify this result by considering this form. Yes, it's not legal trick, but I will justify it later, because let us imagine, because v has to be a function of rho at r is equal to a and vanish at infinity, so we can assume that v has the following form. The v function, oh, this should be vector. V function is here at r is equal to a. Let's assume it's proportional to rho only, and there is some function of r. Then v at r is equal to a is exactly this, because this is constant, so it's rho times this function satisfies this condition. And for r is equal to infinity, if r vanishes, the second condition is also satisfied. So the first condition is r at a is omega, and the second is the first is r at infinity is 0, and the second is r at a is equal to omega, this translation. So let us substitute in this form of v. So this is gonna be minus v, and there is derivative with respect to r, so that's minus rho r prime theta hat plus v with respect to rho, which is v with respect to rho, which is r times z plus rho r prime z, and there is 1 over rho plus this, which is 2 times this. So let's do actually here. This is the expression, and now we have to take another curl. So the next thing we will do is this, and I think there should be no r prime here, because we are differentiating with respect to rho, so it's only this part. I'm sorry. Next we will compute this. So curl of rho, oh, let's take out the minus sign, so it's this 2rz, and that is curl of rho, which is what? Which is you can nabla of rho, which is rho hat, cross theta, which is what? Which is rho hat, and theta are in positive direction of phi, and there is a sign because we are using the cross product, so it's their magnitude times the sign. So this is gonna be r prime sine of theta phi. The next is nabla acting on r, which is r double prime r hat cross theta, which is r hat cross theta, it's plus phi, that's plus phi, it's rho double prime phi, yes, that's it, plus, and again there is cross product of theta, which is gonna be from the table 1 over r times phi hat, which is 1 over r rho r theta hat minus a curl of this, which is going to be easily computed because it's minus r cross z, which is again a mixed condition. R cross z, it's a negative direction of phi, so it should be minus, minus, and minus. It will give plus sine plus 2 r sine theta of z of phi vector, and the curl of z is 0. Let us think about more of these terms, because they are the same, because these three, because the sign is related with r, with this relation. So this is gonna be rho over r, and this is also rho over r. So this is the same case as in Stokes' law derivation we have dealt with before, so it's so easy for us. So that is gonna be rho. We can take before the bracket, and there is r double prime, and there is 1, 2, and 4 plus 4 r prime divided by r times theta times phi hat. That's very easy. I can say that it's I can write it like this. It's rho times some function q, for example, times q is a function of rho only. Next, we have to take a curl of this and equate it with a pressure, but we don't have to do that, because pressure cannot be a function of phi, because otherwise there would be discontinuity. But if it's not a function of phi, so the gradient, there should be a gradient. The gradient of the pressure is not proportional to phi hat. Yes, and if it's not proportional to phi hat, this should be 0, because otherwise it would be something, at least. So this should be 0, so the q is 0, so this is 0. So this is 0, that's Euler equation with characteristic equation lambda lambda minus 1 plus 4 lambda is equal to 0. Again, we are substituting in the solution r to the lambda power, and you will get this. So the solutions are lambda is 0 and lambda is 3. So the solution for r of the as the function of r is a over r cubed plus b. Again, we will use the boundary conditions given here. R at infinity should vanish, so b should vanish, and r at a is equal to omega, so this is gonna be omega times a cubed over r cubed. So this is our function r. Immediately from this you will get velocity field from the assumption we have made right here. Clearly though, the assumption have turned out to be true. Velocity field is linearly proportional to rho, and it's rho times r, which is omega a cubed over r cubed, and there is phi hat. That's this velocity vector. We have to now compute from this velocity vector field the torque or the moment of force exerted on the spherical body, it will be really easy, but you have to compute the stress tensor, which is again defined by this constitutional relation. So it's minus pressure times identity matrix, eta viscosity, dynamical viscosity, plus gradient of V plus gradient of V transpose. No, that's nothing. So that's our constitutional relation. Now, for the pressure, we have assumed that it's going to be 0 at infinity. Oh, we have not, but there is another condition, boundary condition, and the third one is the pressure at infinity is equal to 0, at R is equal to infinity is equal to 0, so the pressure has to be 0 everywhere, because the pressure is function of no variables. Otherwise there will pop up some vectors, some more vectors, because the gradient is proportional to unit vectors of its linear combination of unit vectors of its functions in P, or the coordinates in P. So there is no dependence on anything, so P is actually 0 everywhere. So this is gonna be this. We have to compute the gradient of V. So let me do this. It's simple. It's gradient of this function. It's rho omega this function a cubed r cubed phi hat. This is really easily computed, because you have to compute nabla rho, nabla 1 over r cubed, and phi hat. That's gonna be rho hat tensor product with phi hat minus free derivative of this, which is minus 3 times rho omega a cubed over r to the 4th power, and there is r hat phi hat, and again we have to compute the gradient of unit vector phi hat, which is gonna be minus 1 over rho times phi hat rho hat. So this is minus 1 over rho, that's omega a to the cubed 1 over r 3, the 3rd power, and there is 1 over rho, so the rho cancels out, and there is phi times rho hat. Yes, again it's minus 1 over rho phi hat rho hat. If we sum this relation with its transpose counterpart, we will get, interestingly enough, this part will cancel with this part because they are antisymmetrical. So the result will be minus 3 rho omega a to the 3rd power over r to the 4th power times rho hat phi hat plus r hat, I'm sorry, r hat phi hat plus phi hat r hat. Yeah, that's the relation. Next we have to compute the moment by integrating it along the surface of the sphere. If you imagine a small portion of a sphere, there is little force acting on this little surface with the surface area ds, and we have to take only the direction in phi hat, and normal vector to the sphere is r hat. So this is the force T with superscript n hat associated to the surface with unit vector n, and by definition of the stress tensor is going to look like this, and component, phi component of this vector, it's going to be its dot product with this vector, so it's this, and because this is row hat, it's gonna look like this. And for a differential moment, or the small moment, it's in this direction, it's going to be rho, which is the distance between the main axis of the sphere and this, the force, and this is perpendicular because it's only phi component, it's perpendicular, so it's rho times no sine function, so rho, or sine of pi over 2, it's rho times this times element of the surface, because this is not force but force per unit area, to be precise, to be more precise. So we have to now integrate it. So the actual moment, it's going to be the integral of all moments. So it's integral, the surface integral of rho at r is equal to a. So it's a times sine of theta, and there is r dot stress tensor dot phi, which is equal to this times from the constitutional relation times dynamic viscosity. So it's actually minus 3 rho omega eta a cubed over r to the 4th power, which is 1 over a, and r is actually a times sine of theta. This cancels out, and there is the dot product between r hat and phi hat. The only term is this will vanish, so that's 1, as you can clearly see, and ds it's going to be a squared, the Jacobian of spherical coordinates, sine of theta d theta d phi can be easily computed right now, because this is not dependent on phi, so it's 2 pi times a squared, 2 pi a squared times 3, which is actually 6, times omega and eta times the integral of sine to the cube, to the sine cubed e theta. And this is a really easy integral, because it's, if you integrate it, you will get 4/3, because its primitive function is minus cosine theta plus 1/3 times cosine to the cubed power, so it's 2 minus 2/3, and this is going to be our moment, which is minus should be there, minus 4/3 times 6 is there is 6 and there is 3, so it's 2 times 4 is 8, so we will get the final result that the moment is 8 times pi a squared eta omega a squared. I think it's correct, but I don't know whether this is a squared. Derivative is 1 over there is 1 over a times a, which is 1, and a squared, and there is another, there is actually a times a squared, so it's a cubed. I'm sorry, a cubed. There is a cube. So this is our moment, and as you clearly see, it's negative, so it means that the fluid is actually slowing the motion of the sphere. You can then compute the motion of the sphere from the second Euler equation, which is this, or this is the same. This is the same equation, so it's going to shade out exponentially. The velocity will go to the zero, it will tend to the zero. There is inertia of the sphere, which is 2 over 5 m a to the 2 power. And also, this is the result we were supposed to show, and I think there is a mistake in the writing. The actual moment is -8. I'm sorry for that. This is the moment exerting on a sphere, -8 pi a cubed eta and times omega. I hope you enjoyed this video. Maybe next time torque on a spinning sphere we have computed in this video. As you can see, it's not so difficult if you know the tricks, and if you have this chart of gradients and divergences and curls of coordinates and their unit vectors, and if you know some rules of vector calculus. So bye, have a nice day.